Okay, good evening. So this is our second lecture for the course Fundamentals of Multiphase Flow. So in the previous lecture we have started our discussion on the definition of multiphase flow. Okay, and if you recall, a special case of multiphase flow was discussed, which is particularly called as two-phase flow. And in case of two-phase flow, we will be having the participation of either two phases of a substance, or we will be having the presence of two different components. Okay, and again in case of two-phase flow also, both the fundamental conditions of multiphase flow should be satisfied, and in case of two-phase flow, depending upon the association of the phases, we have seen that we can have either well separated flow condition, or we can have well dispersed flow condition. Okay, in case of well separated flow, one phase can be distinguished by a distinguishable boundary, interfacial boundary, from its continuous phase. And in case of well dispersed flow, the two phases are kind of intermingled in such a way so that we cannot specify a clear boundary to distinguish the two phases. Okay, and with the help of this example, we have seen that first feature of the flow is that there should be presence of at least two or more phases. Second point, it is a multi-scale phenomenon, because inside a continuous phase we can have entities of different sizes, so that makes it nothing but a multi-scale phenomenon. And third point was multi-physics problem, because within a single tube we can have phase change heat transfer, we can have reaction also participating in the medium, we can have other applications such as electric field, magnetic field connected to a single device. So that's why, because of these kind of situations, multi-phase flows, or in special case two-phase flows, are of multi-physics nature. Okay, now there are different types of multi-phase flow. So for example, if you have to classify two-phase flows, okay, so how you can classify two-phase flow? You know that there should be either presence of the two different phases, or there should be presence of two different components. Okay, so in terms of two-phase flow, what are the different combinations possible? So you can have a single physical domain, and in that single physical domain there can be presence of gaseous phase as well as the liquid phase. So when we will be having the presence of gas and liquid, then I can specify that particular two-phase flow as nothing but gas liquid two-phase flow. Okay, then I can have other combination where gas is participating with solid particle. That type of flow I will be calling as gas solid two-phase flow. Okay, then third combination I can have where I have liquid and solid present in the system. Okay, then I will be calling it as liquid solid multiphase two-phase flow. Okay, so can you give me some examples of gas liquid, gas solid and liquid solid two-phase flows, which you can see from various industrial or natural occurrences? Water and water vapor. Okay, so if you see the presence of water and water vapor, applications are plenty. You can talk about a coal-based thermal power plant. In case of coal-based thermal power plant, particularly in the boiler section, you will be having liquid phase as well as the vapor phase, which are actually interacting with each other. Okay, in the condenser of the same power plant also, there will be combination of liquid as well as the vapor phase. Okay, if you go to a nuclear power plant, your overall cycle remains the same, only change is in the addition of heat source. Okay, so in case of nuclear power plant only, where in case of a coal based thermal power plant you are having actually the coal fired furnace, in place of that you will be having some nuclear reactor core to supply the energy. So the mode of energy which is coming to the working fluid, that is changing, whereas the nature of the cycle is remaining the same. Okay, so in the boiler as well as in the condenser, you can find that there will be combination of liquid water, because in boiler what happens, in boiler of a power plant, at the entry point liquid comes in the saturated state, and then further addition of heat transform it into vapor phase. Okay, so you have combination of liquid and vapor. Similarly, in the condenser what happens, you have saturated vapor at the entry point, and at the exit point you will be having pure saturated liquid, and in between the condenser you will be having combination of the liquid and the vapor. Okay, so similarly you can see your domestic refrigerator, that is nothing but the reverse of a Rankine cycle which is used for power plant. So in Rankine cycle your working fluid is changing, and the way flow of refrigerant is happening, that direction is just reversed. So there also in the condenser and evaporator you will be having the presence of two phases. Okay, likewise even you can see a common example. If you take a glass of water and if you start pouring water into the glass with the help of a bottle, what you find that if you consider a transparent glass, you will be seeing from the side when you are pouring water inside that there will be formation of small bubbles inside that water. Okay, so that is also nothing but a gas liquid two phase flow. Okay, now next comes gas solid two phase flow. Can you give some example where you can see the presence of gas liquid gas solid two phase flows? Cyclone, yes. In case of cyclone what happens, you have wind, and wind is actually carrying the rotating wind is carrying the dust particles. So dust particles are nothing but the solid phase, and these particles are actually continuously rotating inside the with the gas. Okay, other examples, this is natural example, coal gasification. So whenever you do the gasification of the coal, you are having a device which is called as gasifier. Okay, so inside the gasifier you have put solid coal particles, and these solid coal particles, then you are supplying some amount of air from the sides, and because of that air these particles are suspended because of the flow of air, and there is some interaction between the suspended solid particles and the gaseous phase. Okay, so that is nothing but kind of a gas solid flow. Another common example is, if you see coal based thermal power plants, so typically in a thermal power plant what we do, we burn coal, and once we burn coal we know that as a byproduct of that we get some ash. Okay, so two types of ash we get from the plants. One is called as fly ash, other is called as bottom ash. Okay, so typically if you see a coal sample does not constitute the complete volatile matter. If it has complete volatile matter, then as a byproduct we will not get any solid waste. Okay, but typically when the coal is actually kind of obtained from the coal mines, in that case we see from the coal mines where coal is obtained, from where the coal is actually obtained after digging the coal mines, we see that coal sample contain 30 to 40% of the non-combustible matter, non-volatile matter. It can be present in the form of sand, stones, many other substances. Okay, so typically when the combustion of the coal is done, the volatile or combustible part of that reacts with the air, which forms the products of combustion after releasing the heat. Okay, and the products of combustion formed by the reaction of volatile matter with the air are nothing but the gaseous products of combustion. These all are in the form of gases. Okay, but the part of the coal which is not participating into the combustion process, that particular part of coal will be actually coming in the form of solid waste. Okay, so you see when you burn wood, once you burn wood, what you get? You get ash. Okay, you get ash. So ash is nothing but the solid waste present in that wood which is not combustible. So in the similar way, in coal also there is some solid particles which are not combustible. Because of that, if you burn the combustible portion, then you will be having the remaining as ash. So two types of ash is there. One is fly ash, second is bottom S. Okay, so inside the this furnace of a coal based power plant, you will be having some forced flow of air. So, and that forced flow of air is then mixing with the, typically nowadays majority of the coal based thermal power plants are having some pulverized coal burners. So pulverized coal burners means coal is supplied in the form of fine powders. Okay, so you will be finding that after the combustion process some particles will be there. Whenever the products of combustion gases are flowing out of the furnace, these will carry some solid particulate matter with that. Okay, so the solid particulate matter which is carried by the exhaust gases, once it is trapped at some location, that is called as electrostatic precipitator, okay, or bag filter. So typically two types of common filters are used in industry, typically in coal based thermal power plants. One is called as electrostatic precipitator and other is called as bag filter. Okay, so whenever, because whatever your products of combustion are coming out of the thermal power plant, you cannot directly dump it to the ambient. What you have to do, you have to clean to the extent as much as possible. Okay, so that's why first solid particulate matter is actually removed from that. So solid particulate matter is removed with the help of electrostatic precipitator or bag filters. Okay, so what will happen at the input, you will be having some gas which is loaded with the solid particles, and at the output you will be finding that solid particulate is trapped at the filter and only gas is actually exhausted to the ambient. Okay, so the collected solid particulate at the filter is something which is called as fly ash, and this is of very fine size, typically present in the powdered form. On contrary, the portion of the coal, uncombustible portion of the coal, which your gases cannot carry because it is heavy in size, which is just falling at the bottom of the furnace, that is called as bottom ash. Okay, so typically if you have a Indian coal sample is having 40 to 50% non-combustible matter. Out of this non-combustible matter, you will be having around 80% of the portion in the form of fly ash and remaining 20% portion in the form of bottom ash. Is this point clear? Now your this fly ash is a product which is byproduct which is used for many purposes. So some people use it for brick making, some people use it, is also used as, in very small fraction, it is also used as a raw material for cement. So in cement industry also people use it. Okay, so that's why what is typically done in a thermal power plant, the place where fly ash is collected, from this place to a place outside the plant, it is carried in some pressurized pipelines, and these pressurized pipelines are nothing but contains high pressure gases in which this powdered fly ash is mixed and then it flows through that. So that particular type of pipelines are called as pneumatic conveying pipelines. Have you understood this point? What are pneumatic conveying pipelines? Because why conveying? Because we are conveying the powdered form of this fly ash from one location to other location. That's why conveying. And pneumatic word is coming because we are taking the help of air. Whenever we take the help of water, then we use the term water or other liquids, then we use the term hydraulic. Whenever we are using the gas, then we say the term pneumatic. Okay, so some pneumatic conveying pipelines are used for transportation of this fly ash in the power plants. So you can see near the pneumatic conveying pipelines, if you go, then if there is some leakage in the pipeline, you will be seeing out of that lots of ash is actually coming out. Okay, because inside pipe is pressurized. Typically there are two other systems that subsequently I will discuss. In some systems are vacuum based, some systems are pressure based, but for large length typically pressure based systems are used. Okay, so other utility of pneumatic conveying pipelines also comes in this pharmaceutical industry. Okay, in pharmaceutical industry, different chemicals are taken in the powdered form and these are conveyed in the proper composition and mixed together to form your medicines. So there also pneumatic conveying pipelines are used. Okay, you can also see the you can also see the application of gas solid flows in different medical devices. For example, if you see your inhalers, in case of inhalers, what you do? You put some powdered form of medicine and then you inhale. Once you are inhaling, then that powdered form is actually coming with the air and entering inside our body. Is this point clear? So all these are nothing but the applications of gas solid two-phase flow. Then we have next liquid solid two-phase flow. So can you tell me some example where liquid solid two-phase flow can be found? Yes, sewerage sludge. So in case of sewerage sludge, you will be finding presence of solids, lots of solid waste which is actually suspended in the water and then it is actually flowing through the pipeline. Then if we go to the more technical application, then you have seen this thermal power plant. So we have seen bottom ash, 20% bottom ash was also there. So these bottom ash particles are actually very hot because these are collected just below the furnace. So these bottom ash particles are mixed with water in a thermal power plant and then these are actually flowed through some pipelines. Okay, so that is the case of a hydraulic conveying. Hydraulic conveying lines. Okay, so these are, if you have two associations, if all three phases are present in some system, then I can call this as nothing but a three-phase system, where you can see the presence of solid plus liquid plus gaseous, all three phases. Okay, then we can have even a three-phase system. Okay, typically, hypothetically, if we see the triple point of water, what is triple point of water? At triple point of water, we will be having the ice as well as the liquid water molecules as well as the water molecule in the gaseous phase. Okay, so similar situations you can also see in various applications where actually you will be having the presence of simultaneous presence of three different phases of a substance. Okay, now based on this classification, let us try to see what are the different possible combinations for gas liquid two-phase flow. So you can see in case of gas liquid two-phase flow, at the entry of the pipe I have pure liquid, okay, and when I moved further downstream, then I am seeing that there is formation of small bubbles, okay, and after that these bubbles are growing in size. Once these bubbles have grown in size, these will be joining together and then forming a gaseous core. So this is nothing but at the center I have gas core and liquid is present either in the form of droplets in this gaseous core or it is present as a film along the wall of this tube. Okay, so typically you can see this type of transient two-phase flow in your condenser or boiler. So inside condenser, what is there? You have lots of tubes. Inside these tubes at the entry point, saturated, sorry, in case of a boiler, saturated liquid is entering and then you are adding heat from this side. So once you add the heat, that liquid is actually converting into vapor. Once it is converting into vapor, it is taking the form of small bubbles. So when bubbles are of smaller size, these are kind of represented by almost spherical shape. Okay. On contrary, once these grow in size, then depending upon the inertia, these can have different shapes. So this is just idealistic representation of gas liquid two-phase flow in a pipe. Okay. And in this particular two-phase flow situation, what is happening? You can see that at different sections of the pipe, the phase distributions are actually different. Okay. At entry you have pure liquid, then you have some bubbles which are dispersed. So here it is nothing but kind of dispersed flow situation. After this, here you have kind of separated flow situation where water is separated, as well as you have some dispersed liquid droplets also present in the gases. Okay, so this type of two-phase flow, which is actually time dependent, that is called as transient two-phase flow. Is this point clear? On contrary, if you have some situation that if you don't focus on the entire tube, if you focus on some portion of tube where flow is actually well separated, then I can have the situation of separated two-phase flow. Okay, so here liquid is at the bottom, gas is at the top, and I am having some clear interfacial boundary between the two. In second situation also, I can call this as a separated flow, because whatever the gas is present in the liquid, that is actually in larger lumps, and I can clearly define the boundary in between the gaseous and the liquid phase. So that's why I am calling it as separated two-phase flow. Okay. On contrary, if you see the dispersed two-phase flow, so here you have some continuous liquid phase, and in this continuous liquid phase, small gaseous bubbles are actually dispersed throughout. Okay. Similarly, in the second combination, continuous phase is actually gas, and in this gaseous continuous phase, I may have some liquid droplets present. If I have liquid droplets present, then I will be calling it as gas liquid droplet flow. If I have gas and solid particles present, then I will be calling it as gas solid two-phase flow. Is this point clear? All are clear with this idea. So why I am repeating these concepts again and again? Because whenever we will be applying the mathematical models, then depending upon the physical distribution of the flow, we have to choose what type of model we should apply. Okay, because when you have dispersed flow, then you have to go for some different kind of mathematical modeling. When you are having separated flow, then you have to go for some different kind of mathematical modeling. So how to do that, that we will be discussing in the subsequent slides. But before that, we should have the knowledge of different types of flows which we can encounter. Okay. Then if I have to define the two-phase flow, then of course I can also have some classification based on the nature of the system present. So in one situation I can have adiabatic combinations, and in other situation I can have phase change processes involved. Okay, so in adiabatic situations, what will be happening? It is nothing but no heat transfer is taking place, but there are either two phases or two components which will be simply interacting with each other because of the hydrodynamic conditions. So here, whenever I will be discussing the adiabatic two-phase flow problems, my only interest will be in hydrodynamics. What is the meaning? That I will be only interested in continuity and momentum equation. I am not interested in solving the energy equation or any other type of equations. Okay. On contrary, if I have say phase change system present, in that case I have to actually, along with the continuity and momentum equation, I have to solve energy equation, and then that energy equation should also take care of the phase change models. Okay, and phase change situations, you can see boiling, condensation, melting, solidification, and sublimation and deposition, and you can see the sector wise applications are also listed over here. So you can go through this slide. This is just for the information. Okay. Now some occurrences. So of course till now whatever I have represented to you all was in the form of schematic representation. Okay. But now these are some of the real time experimental videos. So here you can see In the first case you have a thin wired heater, okay, and in this thin wired heater we are passing some current through this. Once we are passing through some current through this, so because of the joules heating, some heat is generating at this point, okay, and I have nothing but saturated water here. So if I have water in the saturated form, if I add heat to saturated water, what will happen? Its phase will change from liquid to vapor. So that is what we are experiencing, that on this heated surface vapor bubbles are actually generating, okay, and these vapor bubbles are, you can see the complete cycle. First vapor bubble is very small in size, then it is growing, and after its growth, once the buoyancy force is sufficiently larger than the surface tension force, then actually it is leaving the surface and rising because of the buoyancy, okay. So this is the typical situation of a nucleate boiling. All of you, if you recall your basic heat transfer course, so this is nothing but situation of a nucleate boiling. So in this situation, it is very important to determine the number of sites at which these bubbles are forming. What is the size of the bubble? How much size of the bubble means size of the bubble once it is leaving the surface of the wire, okay, because if bubble stays for longer duration at the surface of the wire, because of the low thermal conductivity we will be having low rate of heat transfer. What is our interest? Our interest is, say, bubble should form and it should immediately leave the surface, because if it is immediately leaving the surface, then that bubble will be replenished by the fresh liquid which is having higher thermal conductivity. If fresh liquid is contacting the heater surface, then rate of heat transfer will be high. So in order to analyze this process, you should know the bubble dynamics. Means you should know that what should be the initial time which is taken by the bubble to reach the size at which it is departing the surface. If you add some surfactant to this system, what surfactant will do? It will reduce the surface tension, okay. Once surface tension is reduced, then bubble at smaller size also will try to leave the surface, okay. Ultimately we have to control the combination of buoyancy and the surface tension forces that is responsible for departure of this bubble from the surface, okay. So this is something very important application. Then in second case, you can see this is the case of a film boiling. So here what is happening? Vapor bubbles are growing in size. Bubbles have, before leaving the surface, these have actually, bubble growth is so fast that two bubbles are merging with each other and forming a blanket of vapor. So here you can see this is a blanket of vapor, and the heat transfer is taking place from this blanket of vapor. So this is the case of a film boiling. So typically in majority of the situations we want to avoid the film boiling because it increases the temperature of the heater surface to extreme limits, okay. Because once the vapor blanket is formed, then what we will be having? We will be having lesser rate of heat transfer in some transitional regime. But if we go for very high temperatures, then of course radiation phenomena become prominent and we will be having further rise in the heat transfer, which we typically see in our boiling curve. So we will study all these details subsequently in this course, but here I am just trying to highlight you the importance of the multi-phase flow, why we need to study multi-phase flow, okay. Then third example you can see over here. So this is a third example. Here you can see this is a copper tube, and on this copper tube we have some surrounding vapor medium, okay, and this copper tube is actually cooled from inside. So once it is cooled from inside, what will be happening? This vapor will be converting into the liquid form, okay. So if these liquid droplets are staying on the surface of the copper tube, these will form a film. Once film is formed, my condensation process will become Which type of condensation process? Film wise condensation process, which is again having lesser rate of heat transfer. So our interest here is once the vapor bubbles are forming, these should immediately leave the surface so that our condensation process can stay in drop wise mode. Okay, so again a typical example of two-phase flow where what they are showing is they have done some microstructuring, and with the help of these microstructures they are actually trying to remove the droplets as fast as possible so that there is no formation of the film. So our condensation process should stay in the drop-wise mode. Is this point clear? Then you can see, so you can see all these applications where actually you are having the requirement of knowledge of two-phase flow. Then another common example. You can see this one. What is happening here? Can you see? Follow the cursor. So you can see this is nothing but intake of a pump, and in this intake of pump, whenever water is being sucked through this pipe, some amount of air is entering into this intake. Okay. Once this air enters into the pump, it will lead to some detrimental effects at the pump surface, at the blades of the impeller of a pump. So in this situation, our interest is to avoid or mitigate the formation of this free surface vortex. Again a case of gas liquid two-phase flow. Okay. Then next is, this is nothing but the internal structure of a Coriolis mass flow meter. Okay. So typically a Coriolis mass flow meter is U-type or any other type of tube structure through which water flows, or any other liquid whose mass flow rate which we want to measure that flows. Okay. So once that fluid is flowing through the tubes are actually flexible depending because we have provided some bends. So because of the Coriolis action there will be oscillations of the tubes, and depending upon the mass flow rate of the fluid, the number of oscillations will change. Okay. So if we count these oscillations of the tube, then these can be correlated to the measurement of the mass flow rate. Okay. So here what I want to show is that if your instrument is designed for one particular type of application, and if in that some intrusion of the air takes place, how it can be detrimental for the accuracy of the measurements. Okay. So typically if you see, in case of a Coriolis mass flow meter, if you see the cross section of the tube, so cross section of the tube will be something like this. Okay. So this black color is nothing but cross section of the tube, and this green point over here shows the centroid of the tube as well as geometric center of the tube as well as the centroid of the fluid medium which is passing through it. Okay. In case of a single phase flow. So if you have pure liquid of same composition flowing inside the tube, then each and everywhere your fluid mass distribution will be same. So that's why centroid of the fluid, this green colored point, will be exactly coinciding with the geometric center of the tube. Okay. So you will be having this type of flow. Once, so this is the oscillation. So here, depending upon the oscillation frequency of the tube, you can say that the oscillation frequency of the tube is exactly equal to the oscillations of the liquid which is flowing in the pipe. So our measurement will be accurate. On contrary, if I have presence of air bubbles of high viscosity, sorry, I have some other medium present with it, it may be liquid or it may be a gas, but the characteristic of this medium is that it is of high viscosity. So now we don't have, at any cross section point, we don't have pure medium present. Okay, there is some other medium present. So because of the presence of this other medium, the homogeneity of the distribution of the liquid is disturbed within the tube. Once this is disturbed within the tube, we will be finding that centroid of this and the geometric center will have some difference. Okay, and once oscillation is happening, of course that external agent will also oscillate. So depending upon its oscillations, we will be having some difference. So you can see over here, you see now the geometric center and the centroid are actually moving differently. Okay, but still, because viscosity is high, so because of the high viscosity, this external fluid is not actually, or entrained fluid is not oscillating much. So though I have difference between the two, but still there is good close match. Okay, enough match. So in this situation, though I will be having some error in the measurement, but error in the measurement will be less. On contrary, if you see a low viscosity system enters, then what happens? In case of low viscosity, the oscillation of the entrained medium will be large. Because of that, there will be significant difference between the centroid and the geometric center. Because you can see, whenever lighter phase is going above, then centroid of the fluid is shifting down. When lighter phase is going down, then centroid is shifting up. Of course, because more weight is at the bottom portion, when it is at the top, when it is at the bottom, more volume is at the top portion of the heavier phase. So because of that, centroid is oscillating. And in this case, you will be finding that because of the large oscillations, the difference between centroid and the geometric center of the tube will be large. And this will give significant error in the measurement. Once it is giving significant error in the measurement, this type of effect is called as actually decoupling effect in Coriolis measurements. So here you can see that if your system or device is designed for one particular application, and into that device if intrusion of the two-phase flow happens, then how it can actually disturb your measurements. So it means that in certain cases it is required, two-phase flow is required, but in certain cases it may be detrimental. Okay, so this is one application where it can be detrimental. Is this point clear? Now I have given you very small scale of examples. Typically I have tried to keep these technical, but other than technical also you can find enormous occurrences of two-phase flows in your day-to-day activities. Okay, whenever you cook food, okay, if you are making tea, then what happens? You have formation of bubbles at the pan surface. Once you put tea leaves inside that, then formation of bubbles increases drastically. Okay, then you are pouring water inside the bottle. Means whatever activity you see, you are taking bath in the morning, so in the shower you can see that fine droplets are coming. So fine droplets of liquid are falling down, and these are falling in gaseous medium. You can see fuel injector of a IC engine or any gas turbine engine. What is happening in the fuel injector? You have fine droplets of the liquid fuel which are actually entering into the surrounding gaseous phase. And depending upon the size distribution of these droplets, there will be evaporation of the fuel and there will be decrease in drop size. That drop number size distribution actually significantly controls the surface area of the liquid fuel. If you have more finer distribution of the droplets, your surface area will be more, there will be fast heat transfer. So it means fast vaporization and good combustion. On contrary, if you have a large lumps of the fuel, then the available interfacial area for heat transfer will be decreasing, which will be decreasing the rate of heat transfer and improper combustion. So that is the reason we invest too much amount on improving the atomization system or fuel injection system in our different types of devices like gas turbine engines or internal combustion engines, so that we can improve the combustion process. Okay, so all these are nothing but examples of the multi-phase flow. So that is the reason that multi-phase flow is having so much vast scale and so much vast nature of problems, because of which it is of multi-physics. So that's why knowing the complete multi-phase flow for a single person is not possible. So in whatever area of interest you are working, actually you should have the knowledge to process uh, the work in that particular direction. Okay, so that is the reason the title of the course is Fundamentals of Multiphase Flow. Means in this course we will try to give you some initial knowledge so that you can further penetrate in any particular direction. Okay, is this one clear? Okay, so typically then you can see in case of gas solid two phase flow, I told you earlier where the occurrences can happen. Now in case of gas solid two phase flow, further there can be categorization. Either particles can be very sparsely distributed in the gas, like in first case. So you can see one particle is here and then other particle is at some different location. So particles are far from each other. Okay, so in this type of case you will be finding that there is no particle particle interaction. So particle particle interaction is not there. So majorly the interaction of the solid particles will be with the surrounding gaseous phase. It may be gaseous or it may be liquid. So I am just talking about over here, say for gas solid flow. So let me call it as a gaseous phase only. Okay. So in this case, whenever you will be developing the governing equations to study the motion of particles, you will be only considering the hydrodynamic effects because of the gaseous phase. You will not be considering any momentum exchange because of the particle collisions or particle interactions. So this is a typical example of dilute gas solid two phase flow. Then there can be one another extreme where you can see this is a tube. Here you can see a dense structure of particles is there. Okay, and if you zoom in into this portion and if you enlarge, then you can find this big picture, and in this big picture also here you can see a completely black region is appearing. If you further zoom in into this portion, you can see so much densely packed particles are here. This is the very densely packed bed. In this case, particles are so closely packed that gases present in the void have minimal effect on their interaction. Majorly the interactions of the particles are driven because of the particle particle interactions. You can see typical example of when you are pouring your say wheat flour in a box. So of course wheat flour are nothing but these are also particles at the microscopic level. So if you see between the wheat flour particles, there will be some void spaces which we cannot see. Okay, but when you are pouring, it is only the particles are flowing because of their interactions. The effect of surrounding gaseous phase is not actually affecting their dynamics. So this is a typical dense two-phase flow. Okay, so when you will be, because this is important to know, because when you will be developing the models or you will be trying to do the mathematical analysis of dilute two phase flow, you will not be considering the particle particle interactions. Of course at certain points near the walls there can be interactions, but with suitable accuracy you can actually with reasonable accuracy you can neglect these. Okay, on contrary, when the particle fraction has increased, then you can see that you have to consider the particle particle interactions. But once the particles are extremely packed, then you can simply neglect the effect of the surrounding gaseous phase, and into your mathematical modeling you can simply consider the interactions of the particles. Okay, so these are the different things which we have to actually consider, and of course one by one we will try to see some idealized situations for mathematical modeling in the subsequent lectures. Now this is another case of liquid solid two phase flow. So in this liquid solid two phase flow, this is the case of a sediment transport pipeline. So where In liquid, we have actually injected the solid particles and we are kind of allowing this to flow. So you can have one arrangement where particles are kind of homogeneously distributed. Okay, so this type of arrangement is called as homogeneous flow. So in case of homogeneous flow, if you see the concentration profile of particle, okay, means volume of particles divided by the total volume of the container. So it is having almost uniform profile. So everywhere you have uniform profile. So CV over here referred to as volume fraction, and volume fraction is defined as volume of particles divided by volume of cell or container. Okay. So when particles are homogeneously distributed, whether you consider this much portion or this much portion, everywhere you will be finding almost on an average you will be getting some same ratio. So that's why this volume fraction profile is kind of straight. Okay. And velocity profile, in this case you will be finding that hydrodynamic interaction between the particles are very less. Only interactions of particles are with the surrounding continuous phase. So under the steady flow conditions, all the particles will try to acquire the velocities of the continuous phase. So continuous phase and the particle will have almost the same velocity value. So because of this, you can see the velocity profile is actually perfectly symmetric. Okay. On contrary, if you slightly increase the particle number or slightly increase the particle size, if you increase the particle size, you will see that you will try to get some settling of the particle at the lower portion of the pipe. Okay. And you have some slight increase in the concentration. So here it is slightly larger, here it is small. And in this case, you will be finding where particles are packing with each other, so they will try to hinder their motion. Momentum exchange between them will become significant, because of which in this portion the velocity is less and here velocity is more. So you have some asymmetry in the velocity profile. But in this case also there is no settling of the particle at the bottom. Okay, in this case particles are still hanging in the fluid, but their distribution of volume fraction is actually more at the bottom. Okay, so this type of case is called as pseudo homogeneous flow. Then I have some third category which is called as heterogeneous flow. In case of heterogeneous flow, what is happening, these gray colored particles are those which are present with no particle-particle interaction. Then green colored particles are those which are also suspended in the continuous phase like the gray colored particles, but their spacing is actually more closer. So because of the more closer spacing, what will be happening? Particle-particle interactions will also coming into picture. On contrary, you have third category of red colored particles which have simply settled at the bottom surface. So because of this, you can see there is significant variation in the concentration profile and also the equivalent change in the velocity profile. Okay. Then fourth category, where the fraction of particles settling at the bottom has increased, and we have other two categories. So this is called as partially stratified flow. In case of partially stratified flow, you have highest volume fraction at the bottom and then you have subsequent decrease of volume fraction to the top. And velocity also you will be finding that these bottom particles are kind of sliding on the surface of the tube. So because of their sliding, there will be higher resistance and their velocity is low. On contrary, the portion of the liquid particles which are above, solid particles which are above that will try to acquire the velocities close to the fluid. So that's why you have this type of jump in the velocity at this point. Okay. Then finally you will be having a situation where you have, if you further increase the particle size or more particle loading, then you will be finding all the particles are settling at the bottom. So in the top portion you have no fraction of particles, no volume fraction of particles, 0, and below you have complete volume fraction. So almost entire portion is filled with the particles, very less continuous phase present. So here you will be again finding that bottommost layer is having too much sliding, but in this particular zone whatever particles are there, then because of the higher inertia of continuous phase, these have slightly higher velocities, and then velocities are actually very high in the continuous phase. Okay, whenever you are getting these three flow regimes, heterogeneous, partially stratified and fully stratified, in these cases you will be finding that there is difference between the delivered volume fraction of the particle and the instantaneous or local volume fraction of the particles which are present in the pipe. Okay, if you consider that at the inlet you are injecting particles at the constant flow rate and continuous phase also at the constant flow rate. What is happening when you are moving from inlet to outlet? Particles are trying to settle at the bottom. So if particles are trying to settle at the bottom, then this bottom layer of particles is having lesser velocity. Okay, so most of the particles will try to accumulate within the tube, but fluid is actually leaving at the same rate. So at the outlet we will be finding that discharge rate of particles has decreased, whereas discharge rate of gas is remaining the same. So in this case the delivered volume fraction of the particle, which can be simply defined as the ratio of flow rate of the particle divided by the flow rate of the liquid, that is actually less in comparison to the local instantaneous volume fraction of the particle within the pipe. Is this one clear? Okay, so depending upon the phase associations, these already I have discussed this, but depending upon the phase associations, the major sectors are actually classified. So if you have gas solid, then you have power and process industry. So in power I already explained to you pneumatic conveying system. Then in the combustion process also fly ash particles, coal particles, these are interacting with the gases. And process industry, as I told you about pharmaceutical industry, so there what you have to do, you have to mix different powders at some composition, and then you have to finally get some products ready, okay, at the desired compositions. Then liquid, okay, one phase association which I forgot to include earlier, that is actually liquid flow. So liquid flow is basically a two component and same phase. So if you consider the example of oil exploration, what happens in oil exploration? Whenever you go to the site from where oil is being explored, you will be finding that there will be presence of multiple oils in our raw oil. Okay, raw form, multiple things are coming, because whatever you see at the final product, so majorly we use gasoline, petrol and diesel. Petrol and diesel both are obtained from the same raw material. Along with that, there are other byproducts such as wax, kerosene. Even at the oil exploration sites, we are also having the presence of natural gas, ultimately which we extract in the form of CNG, compressed natural gas. Okay, so it means that there can be situations if you have to bring the raw oil from oil exploration site to your refinery, then you need some pipeline. Okay, so in that pipeline, whenever you will be taking the raw form of oil, that raw form of oil will be having different layers of oils present, and all these layers will be actually flowing in a same pipeline, and then at the refinery distillation or other processes are done in order to separate out the individual products which we can use actually for practical applications. Is this point clear? So this is a system where we can have the different liquid components present, but So here we have two different components, but phase is same, liquid. Okay, so applications are in oil refinery. Then we have solid liquid. So solid liquid, again I gave you example of sediment transport, bottom ash transport. So all these are related to chemical and process industry. Then gas liquid, of course, power industry, everywhere within the boiler, condenser, we have formation of vapor bubbles and the water present. So ultimately, if you see all these things, here also power is coming, here also power is coming, and in order to run a power industry, you need fuel. Fuel is coming from oil refinery. Then in order to run the power industry or chemical processes, where you have solid liquid flow, so this is nothing but a closed loop. So you cannot say that standalone system will be sufficient, okay, because things are nothing but interlinked to each other. So you cannot say that if I know the gas solid two-phase flow, it means I know complete knowledge of multi-phase flow. Or if you know the gas liquid two-phase flow, you can work or you can provide solutions to complete problem of a power industry. That is not possible, because any large scale system, industrial system, if you have to analyze, you should have the knowledge of all the forms. Okay, so that's why this is again important aspect, because of which actually multi-phase problems are also very complex. Again, what I have done over here, I have listed the different applications. These are sector-wise applications, and then specific examples are given. Even you can see in biological system, we have actually multi-phase flow. So respiratory system, I have already given you the example. In case of respiratory system, what happens? That if we take some inhaler, then powder is actually going inside. Also, we have some biological filters present in our body. So if you go to some polluted area, where like Delhi nowadays, so you will be inhaling lots of particulate matter into your body. Okay, so sorry, yes. Then you can see the temperature control using perspiration. So if you see in winters, there is no sweat, but in summers, in order to maintain the temperature of the body, our body itself generates lots of sweat. Okay, so which is coming through the porous structure of the skin. So again, there is nothing but presence of the multiple phases and interaction of the multiple phases. So lots of examples are listed over here. You can actually see for details. Okay, then another interesting aspect is that multi-phase flows are actually counterintuitive. So what is the meaning of counterintuitive? That from intuition, if something is being satisfied for one type of problem, if you simply reverse the situation, you will be finding that same type of behavior will not be there. Okay, one typical example is given over here. So we have one droplet of water, sorry, a droplet of any liquid, and in the surrounding I have some gaseous phase, and this droplet, no, I am writing it wrong. So this is a bubble. I have a gas bubble, and this gas bubble is present in some stagnant liquid phase. So I have liquid in the surrounding and a gas bubble. Okay. So if I consider that the viscosity ratio of the liquid to gas is 10, surrounding liquid and the gaseous bubble viscosity ratio is 10, then Galileo number and the bond number, these are the relevant non-dimensional parameters which are associated to the counteracting forces for this situation. Okay. For example, in case of bond number, what we will be having? Buoyancy effect is balanced by the surface tension effect. In other number, viscous effect is balanced by the buoyancy effect. Okay, so two counteracting effects which are related over here, actually these are combined together. So if we keep the Galilei number and bond number, what are these, what are their definitions, that subsequently we will be studying. So here we have taken the magnitude as 150. So what we have done, we have photographically captured the photographs of this bubble at different time instants. So this is at t equal to 2 seconds, then 3 seconds, 4 seconds. Gravity is acting in downward direction. So of course this bubble will rise like this. So you can see that how there is change in shape of the bubble when it is rising in the upward direction. Okay. Now if I consider a similar situation means if I consider that I have now a drop. This is a liquid drop, and in the surrounding I have a gas. But again this combination is such that so that my viscosity ratio is 10 and Galilean bond numbers are same. So what we will be expecting? We will be expecting that at different time level, of course this will be at now 2 seconds, then 3, 4, 5 and 5.5. Our common expectation is that if we are keeping the dimensionless parameters same, okay, just we are interchanging the fluid, our common expectation is that we will be having similar kind of shape. So I may expect that the way this bubble was looking at 5.5 second, I should have an inverted shape over here. Okay, but this does not happen. So ultimately if you see, these are the actual scenario. So it means this is actually counterintuitive. Now why this is happening, there are further reasons which we will be discussing in subsequent lectures, but typically whenever a bubble rises, there is internal circulation within the bubble which controls its shape. Whenever a drop is falling, drop is actually a higher viscosity liquid, so internal circulations circulations diminishes within the bubble and within the drop, and circulations takes place in the surrounding gaseous phase, which typically changes the shape. Okay, so that's why these things are nothing but counterintuitive. You may think that you are keeping all the dimensionless parameters same, you are just inverting the fluid, so system should behave in a similar manner, but that is not happening. Okay, so that's why it is counterintuitive. Another thing you can see, this is a typical gas bubble, and this gas bubble is actually rising in a stagnant liquid. This is a stagnant liquid filled in a tube. So you can have a tube, in that tube water is filled, say liquid is filled means say water is filled, and you are injecting some air. So once you are injecting the air bubble will be rising in the tube. Okay. Now if you keep that tube at different angles, at what angle bubble will be having highest velocity? Can you tell me? Sorry? Vertical? Horizontal? Horizontal it will not be rising. Vertical. So our common interpretation is that at theta equal to 90 degree of the tube, I should have highest velocity, because corresponding to that situation, what we will be having? We will be having the highest buoyancy force. Okay. But if you see, we observe that nearly close to 45 degree we have highest velocity, and when we further increase the angle, then our velocity further goes down. And at 90 degree it will be even significantly lesser than the velocity at 45. Why this is happening? Again a counterintuitive phenomenon, because our common intuition is corresponding the vertical orientation will be having the highest velocity. What are the reasons for this we will be discussing later, but just one hint I can give you, that you can see the shape of this initial portion. Here you see the nose, here also you see the nose. So basically at 45 degrees our nose of the bubble aligns in such a way so that the drag force, interfacial drag force, is actually least. Okay, once this bubble is rising, there will be some viscous force acting because of the viscosity of the surrounding liquid at the interface. So that viscous force magnitude, our shape of the drop is adjusting in such a way, particularly the leading edge of the drop, so that corresponding to that point we will be having least drag force. So that's why we have the highest velocity. But whenever we have the 90 degree thing, then shape is symmetric and it is more blunt. Because of that, the drag force associated is actually large. Okay, so these are the things. There are thousands of such examples with the help of which we can say that multi-phase flows are nothing but of counterintuitive nature. Okay, so whatever we think from our common intuition that this should happen, that will not be happening. One common thing is, if I consider my, say this is my pressure specific volume diagram of a pure substance, okay, and for this pure substance, if I say that I have a container at this point, this is the state, and this container is initially having some portion of liquid plus some portion of vapor, mixture of liquid and vapor. Now if I, and this container is closed from all the sides, so it means inside this container I will be having nothing but a closed volume process. Okay, now if I add heat, what will happen? Say my container was filled like this. This was the initial liquid level. So below this I have liquid and above this I have vapor. This was the initial level. Now I started heating it in a closed volume system. If I heat it, what should happen? Liquid level should decrease. Okay, that is our common intuition. But ultimately what I will be finding that if I heat it, liquid level will keep on increasing. Though this is very easy. No, you can think it. This is from basic thermodynamics. Yes. So this is a which process? If you are at this point, if you have fixed volume and you keep on heating, what will happen? You will be having heating process at the constant volume. So it means that at constant volume, if you are heating, if more vapor is forming, that will lead to increase in pressure. So your pressure will keep on increasing. As pressure is increasing, the boiling point of the water will also keep on increasing. Once the boiling point is increasing, then there will be new equilibrium. And if you keep on doing this process, you may end up the point where you are having actually pure saturated liquid. No, it can be less than critical point. Say critical point is at this point. Is this one clear? So that's why in case of a closed container, if you start from this point, then what will happen? If you start from this point, then your liquid will be converting completely into vapor. So it means you are having same container, it is just the difference of the position where we are. If we are at less than critical point, then in same liquid container, upon adding the heat, liquid level will keep on increasing. On contrary, if I am at a point above than the critical point, then in the same container my liquid level will keep on decreasing. Okay, so all these are nothing but the different facets of multi-phase flow, and which are kind of counterintuitive also. But this is not that much difficult. This is just from the basic thermodynamics. Is this one clear? What's the time? Okay, so now we will close for today, and we'll discuss further in the next class. So typically from the next class we will be having conversion towards more mathematical oriented things. Okay.